Salts of weak bases and strong acids produce acidic solutions. Let's look at this salt, ammonium chloride. Ammonium chloride is produced when I react NH3 and water. So when I put ammonium chloride into water, it breaks apart into ions, NH4 plus and Cl minus. NH4 plus comes from NH3. NH3 is a weak base, which means NH4 plus is a strong acid. Cl minus comes from HCl. HCl is a strong acid. So that means Cl minus is a weak base and will not react with water. So only the NH4 plus reacts with water. Here's the equation down here. It produces NH3 and H3O. So NH4 plus acts as an acid. So we get a Ka expression. Let's look at an example problem. We have the salt ammonium nitrate. So NH4 NO3, when I put it in water, breaks apart into ions. NH4 plus comes from NH3. NH3 is weak, so that means NH4 plus is strong. NO3 produces NO3 minus. Well, HNO3 is strong. That means NO3 minus is weak. So the only portion of the salt that reacts with water is NH4 plus. So NH4 plus reacts with water to produce NH3, and it's going to act as an acid, so H3O plus. Icebox. 0.2 molar solution of the salts, so 0.2 for NH4 plus. Now, nitrate is still in solution, but it's not going to react with water, so it's not part of the equation. Products are 0. We're going to use variables. Since NH4 acts as an acid, we need a Ka value. Ka can be found by taking Kw divided by Kb. Kw, 10 to the negative 14th. Kb we're given in the problem, 1.7, 10 to the negative 5. So Ka comes out to 5.9, 10 to the negative 10th. We want to calculate the pH. So we know what Ka is now, so we can set up a Ka expression. So 5.9 times 10 to the negative 10th is equal to products x times x divided by 0.2 minus x, and we can use the shortcut. So x is negligible compared to 0.2. When we solve for x, that is the concentration of H3O, comes out to 1.1 times 10 to the negative 5th molar. And then the pH is negative log of that number. So the pH, 4.96, which is acidic. So if I put this salt into water, I produce an acidic solution. The fourth type of salt is a salt of weak base and weak acid. Now in this type of salt, both ions undergo hydrolysis. Both ions react with water. So if I want to know whether the solution is acidic, basic, or neutral, I have to know the Ka and Kb values. For example, NH4Cn is a type of this salt. NH4 comes from NH3. NH3 is a weak base, so NH4 reacts with water because it's a strong acid. Cn comes from HCN, which is a weak acid, so Cn minus is a strong base, so both ions react with water. So you have to compare Ka to Kb. Ka for NH4 is 5.9 times 10 to the negative 10th, and Kb for the Cn minus is 1 times 10 to the negative 4th. So if I compare Ka to Kb, Kb is greater. That means if I put this salt into water, it's going to produce a basic solution because Kb is greater than Ka. We're going to ignore letter I, so you can just mark that off if you want to. Okay, qualitative look at acid strength. We've seen certain acids are strong and others are weak. I've told you there are 6 strong acids. Well, if you go back to the list of 6 strong acids, HClO4 and HCl are both strong acids. They're completely ionized in water. But if we put those 2 acids in diethyl ether, HClO4 is completely ionized, but HCl is only partially ionized. And so this allows us to see that HClO4 is a stronger acid because, by definition, a strong acid completely ionizes in solution. So HClO4 is a little bit stronger than HCl because it completely ionizes in diethyl ether in a different solvent. For binary acids, if we're looking at a group on the periodic table, the acid strength is related to the bond energy of the HX bond. The stronger the bond, the weaker the acid. These are acid strengths for group 7. HF, HCl, HBr, HI. As you go down a group, acid strength increases. So HI is the strongest binary acid in group 7A. So as you go down a group, acid strength increases. For binary acids of elements in the same period, if we're going across the same row, the acid strength increases with increasing electronegativity. So as you go across a row from left to right, stronger binary acids are on the right of the periodic table. Oxyacids. The larger the number of oxygens, the greater the acid strength. Oxyacid has hydrogen, a nonmetal, and oxygen, like H2SO4 as an example. The strength of the oxyacid depends on formal charge. Higher formal charge, easier to remove a hydrogen. So higher formal charge would mean a stronger acid. Here's some examples with the oxyacid HClO4. You'll notice that the formal charge of the Cl, if I just have 1 oxygen, the formal charge is 0. If I have 2 oxygens, the formal charge is +1. And if I go up to 4 oxygen down here, the formal charge is +3. Basically, the more oxygen you have, the stronger the acid. The strongest acid is way down here because if you look at the Ka value, it's rather large. That means it's a strong acid. So the higher the Ka value, the stronger the acid. So HClO4 is the strongest acid out of these 4 oxyacids. In general, we can apply this formula to oxyacids, where E is a central atom, E, O to the M, OH to the N. Basically, again, the number of oxygens indicates the acid strength, so the more number of oxygens you have, the stronger the acid. So if M equals 3, Ka is very large, so that means it's a very strong acid. So the more oxygens you have in an oxyacid, the stronger the acid. And then finally with oxides, metal oxides are basic, non-metal oxides are acidic. And we get the highest metallic character on the left and bottom of the periodic table. So that would be the most basic. So if we're comparing oxides and you want the strongest acid, you want up towards the top right of the periodic table to have the strongest acid.